Is there an actual formula that just
okay.
does it?
In some sense, yes. Okay, so the problem is if we are given n copies of identical Lego bricks, and let's say the bricks are L by W, length by width, how many different objects can you build? So there's a lot of ambiguity in this. So for instance, we talked if big N equals 1, there's only one thing you can do. You just plunk the brick down. But as soon as you're saying that, you're basically saying that the orientation of one brick by itself doesn't really matter. Does that seem a reasonable assumption to make? I don't really care if this is an east-west or a north-south. Actually, this is Williamstown. It's very easy to figure out which way is east-west, north-south. Okay. Once you start having two bricks or more, then orientation could matter. So in some sense, you can always fix the first one, and you choose your coordinate system like that. So this is a course taught in the mathematics department. There is supposed to be at least some mathematics in this. And so I'm trying to use these as a springboard to talk about various things, such as linear algebra. How many of you have taken linear algebra? How many of you will take linear algebra at some point? OK. How many of you remember those painful classes in high school where you did equations of ellipses and hyperbolas? I'm seeing a few. OK. And so if I were to give you a nice ellipse, say oriented like this, and I give you, the major and the minor axes, could you write down the equation for the ellipse? So this is the old x over a squared plus y over b squared equals 1. OK? And you can check, it goes to the point a 0, and negative a 0 goes to the point 0b, and 0 negative b. What if instead of giving you this wonderful ellipse, and now let's see if it will swing back when I come over here. Oh, it does. Excellent. It's working today. What if instead I gave you an ellipse that was at an angle relative to the coordinate axis? So now here is my x-axis, and here is my y-axis. How many of you did this in high school? OK, not many. How many of you know how to do this now and write down the equation for this ellipse? If you've taken linear algebra, you've actually learned how to do this. It all comes down to write things in a good basis and then convert back. This ellipse does not want to be discussed in the standard xy basis. There's a very natural basis for this. The natural basis is this direction, let's call that the u direction, and this direction, call that the v direction. In that coordinate system, we can write down the equation of the ellipse very easily. And then all we have to do is convert from the uv basis to the xy basis. This is one of the big themes of linear algebra. You choose the basis that's most convenient for the problem. Okay? I am a huge Bostonian. I hate most things about New York. But there's one thing I have to admit New York does better than Boston, or at least a subset of New York. Which part of New York do I have to give credit to? The grid in Manhattan. Right? It's very natural to talk about where you are in Manhattan, the north, south, east, west. So here, you would write down the equation of the ellipse in the uv basis, and then you would use a rotation matrix to move from the uv basis to the xy basis. And so it's not that bad. You end up getting, it looks like x, y, and then some matrix alpha, beta, gamma, delta, x, y equals 1. And that's the general equation of an ellipse. So why am I talking about this? I'll choose two 1x1s with different colors. How many ways can I combine them? 2? Why 2? So if I do it like this, the colors might matter. So let me take two grays. So they're supposed to be identical bricks. How many ways can I combine them? Seems like there's only one way, like this. If Kayla almost came to class today, she's a little sick. She's no longer, I don't think she's contagious anymore, but if I were to flip it like this, I would take Kayla and I would actually just flip her upside down. Is this a different combination? I think we should all be willing to consider that this is the same because I can get it just by rotating myself. And if I just rotate, that should not be a difference. So did anybody get an answer other than 1 for two identical 1x1 pieces? One is one of the two correct answers. There is another correct answer for this. Do you have it?
I think we were considering that as one, but as separate ones as also an object you can make.
Okay. What else? What else could you do? You said you had something else you could do?
Well, we just have them separate.
So one thing is you could have them separated. As soon as you have them separated, you could actually have infinitely many different things. So we might want to modify this. Maybe it should be connected. So we'll put in connected objects. Because if they're disconnected, it's really two smaller subproblems. I have a problem of two 1x1s together, and then I have a separate problem of how many things can I do with just a 1x1. Now, if you had ended up having 10, you could, oh my God, I could have all 10 together, 9 together, and 1 separate, 8 together, 2 together, 8 together, 1 together, 1 together, and just going through all those possibilities. Well, really, all that matters in some sense is how many ways can you do when they're all connected. You can do some kind of combinatorics to get the rest. All right. There is still another solution for connected, yes. Infinitely many. How do you get infinitely many? Yeah, so I can rotate this. What's the maximum I can rotate this? What range do I have to allow the angles to go? So one possibility is 360 degrees. What else? 90. Because once I rotate at 90, it looks the same. Can you do better than 90?
45.
Yeah, I think you can just get away with 45. So when you want to try to specify what space of solutions you have, you could parameterize it by they're stacked together, and the first one is oriented, say, along the coordinate axis, and the second one, the angle goes from 0 to 45 degrees or 0 to pi over 4. In order to keep the problem finite, let's assume that all connections must be right angles. Otherwise, we have all these degrees of freedom. So we'll say, how many different connected, right-angled objects do we have? And it's really important to take the time and think, what are you assuming when you start making these questions? So now, how many ways do I have if I gave you 3 1x1s? One. If I give you 4 1x1s? 1. Okay, so at this point, the problem is no longer interesting. Right? The more 1x1s I give you, all I can do is really just keep piling them all up together. So we have a complete analysis in this case. The answer is just 1. Okay? So now, what's the next easiest case to study? So we could do 2x1s. So let's see, I think I have, they're thin, but I don't think it should really matter. So I have 2 2x1s. How many ways can I do 2x1s? 4. All right, why 4?
Each of the 90 degrees along one point.
Okay, so let's see what the best way is to draw this. So we now have 2 2x1 bricks. So the first brick looks like this. How many ways can I put the second piece on it?
2.
Okay, why 2?
Because you can, well, 2 of them would be the same. If there are 4 ways to put it on.
Okay.
2 of them would be the same.
So give me one way to put down the second brick. Directly on top. So one possibility is the on top. All right, so that's one way. What else could I do?
1 over.
1 over, in which way?
To the right.
To the right. So another possibility is 1 over to the right. This is the same as what? The left on the bottom. And so this allows us to introduce a really important concept called chirality, or handedness. Any bio or chem majors here? Okay, have you talked about mirror images of compounds? So sometimes one compound can cure you while the mirror image will kill you. And so there is a handedness. And so if I put it to the right over here, I can twist it down like this. And that's essentially the same as just picking up my daughter and spinning her. It shouldn't change the physical properties. But is there a way to go from this to having it go in the opposite direction just by spinning things? This is the mirror image. So the question is, do you consider the mirror image different? For a lot of things, I would say yes. For some things, you might say the mirror image should not be counted as different. So for now, we'll count the mirror image as different, and then I'll talk a little bit in a moment as to why you might want to consider the mirror image the same. You get to choose which problem you're studying. Depending on how you phrase the question, there will be different answers. And this is why for years a lot of people disagreed as to what the answer was to the problem. Some people didn't assume things had to be connected, for instance. All right, so these two is one way. Then you could, of course, go this way, which equals this way. And then is there something else? I'm sorry?
On the ends, like parallel with each other.
What do you mean by on the ends parallel? Oh, like this? Moving forward 1 unit. And so the last one is I put the second one on top going forward, which is the same as going down on the bottom. So if I give you two 2x1s, it looks like there are only 4 ways up to symmetry where mirror image does not matter. Okay? What you really want to do is you want to start building a table with all the different values of L, W, and N and see, can you sniff out a pattern? Again, I don't care so much about what the answer is for this problem. I want to use this as a way to try to show you guys some mathematics. So I'm going to use this to lead into game theory. How many of you have ever played tic-tac-toe? All right. I believe I am still the reigning champion at the Williamstown Elementary School playground. Have never been beaten by the kids. Occasionally they tie me. So, tic-tac-toe. Now, there are ways to make tic-tac-toe interesting. Standard tic-tac-toe is boring. Okay? How many of you actually know interesting ways to play tic-tac-toe? Okay, which way do you know?
It's like called like tic-tac-toe, I think, and it's like what you have. I think it's like a 4x4.
Okay, so one thing is to make the board larger. That can make things interesting. Anybody know any other ways to make tic-tac-toe interesting? All right, I will. Yes.
I'm not sure if the same thing, but you sort of have like bigger tic-tac-toe board than each box has another tic-tac-toe.
Yes. So one way of making tic-tac-toe interesting is there's a tic-tac-toe board in each square. And then there are several variants you can play. All right. You guys want to play against me? Okay. No, you stay there. You'll be speaking on behalf of the class. Where do you want your first move to be?
I want it to be in the upper left corner of the upper left box.
Upper left corner of the upper left. Do you want to be X's or O's or some other shape? You want to be X's. All right. So Elijah moved in the upper left corner of the upper left box. I now have to move in the upper left box because he moved there. If I move in the center, then Elijah has to move in the center. So wherever you move, you force the next move to be in the corresponding box. So for instance, if I go over here, you now have to move in this box. So where would you like to move?
The upper right corner.
So now you move in the upper right corner. So now I have to move in this box. I'll grab the center. Now you have to move in this box. Where do you want to go?
I would like to go in the lower left corner.
So now you go in the lower left corner. And the game just proceeds like this. And so one way you can play it is whoever is the first one to get 3 in a row in a box wins the game. The other way, I will deliberately play poorly now. So I have to go down here. All right. I will go up here. Where would you like to go?
I would like to go in the upper right corner of the box.
Okay. I will go here. Where would you like to go? I'm deliberately playing poorly.
Go in the lower right corner.
No, you don't.
You could win. Or I could just win, but like it's more fun to get it. No.
Have you seen the beginning of Monty Python where the llama's being sacked? You've been sacked. All right, take over. Where are you going? So one way of playing is the game is now over and I've lost. The other way of playing is that's now an X on your path to trying to get 3 in a row. And then you can play whether or not, if there are still spaces in here, are you allowed to go in there? Or is the cell no longer available, in which case you need some rule that will describe where do you go next. What if there are no moves available there? So there's a lot of tweaks and twists you can do on this. This game is far more interesting. Let's get back to standard tic-tac-toe. I am assuming everybody knows how to play tic-tac-toe. If you don't, just nod and you'll pick it up really fast. Okay? How many opening moves are there in tic-tac-toe? 9. How many responses? So we have 9 times 8. That's terrible 8. 9 times 8 equals 72 opening pairs of moves. Okay? That's a lot. I claim there's far fewer opening pairs of moves. How many opening moves are there really in tic-tac-toe? Not 4. 3. What are the 3 opening moves in tic-tac-toe? I'm sorry? Center was 1. Corner is 2. And then sides are 3. So there's really only 3 opening moves in tic-tac-toe. How many responses are there? Well, we're now going to have to start breaking into cases. Okay? So let's see if the camera will continue to pivot. Oh, wow. It's a good day. So let's say we go in the center. How many responses are there? Only 2 responses. The corners. Okay? We could go in a corner. How many responses are there now? More than 3. 5. 1, 2, 3, 4, 5. And if we go down here, how many responses are there to the middle? It'll be 1, 2, 3, 4, 5. So there's 2, 5, and 5. We're now only 12 pairs of first 2 moves. That's a lot less to analyze than 72. And you can keep doing this to break down the analysis. So it turns out if you go in the middle and someone responds with the middle, you can always beat them. And so you can start really pruning down the possibilities. So there's not that many things you have to learn. So why do you think I'm talking about tic-tac-toe after talking about Legos? How does this connect with what we were doing a few moments ago? What's its relation to this? So we said we're not counting. Yes?
Oh, like it's about the relation to, or like what we first thought was 72 moves.
Right.
Because there are some that are symmetrical, effectively. Then it goes down to 12, which is similar to the Legos being symmetrical, and so rather than having like 8 or infinite possibilities, we have 4.
So you're close. It does have something to do with symmetries, but you need to say a very specific type of symmetry. Which kind of combinations? Could someone close the door? Which kind of combinations? What did we have to be careful about when we were looking at the 2x1s? I'm sorry? Orientation. So we decided when we were counting the 2x1s that we don't care about mirror image. I'm sorry, that we do care about mirror image. The two things that are mirror images of each other should be counted differently. When we're doing the tic-tac-toe analysis, do we care if things are mirror images? No. Right? We're just trying to analyze the games. And so here, when we're trying to count, we don't care if certain things are mirror images. If I go here, 1 and 1 are the same, I can get it by flipping the board about this diagonal. So depending on the problem you're looking at, you will have very different ways of counting. For tic-tac-toe, if two states are mirror images of each other, that's fine. Now, if you live in a two-dimensional world, you can't just flip the board through the third dimension. But theoretically, we can, and we can say this game proceeds analogously as if player 2 moved here instead of moving there. All right, let me show you, or at least describe, two other ways of tic-tac-toe that are fun. One is bidding tic-tac-toe. So you and your opponent each start off with, say, $1,000, and you do a sealed bid on how much the first move is worth to you. Whoever bids highest gets the move. One version has the winning bid goes to the banker and the money is out of circulation. The other, the person who bid lower gets the money. So a lot of times people bid far too much for the first two moves, and then the next person can just win the next 3 bids and win the game. So what's nice about this is you can actually handicap yourself. Let's say you are playing an elementary school kid. You can give the elementary school kid maybe $1,500 and take $1,000 for yourself. And you can make tic-tac-toe a reasonable, fun game now. The better you are, the less money you give yourself to start with. The more sense you have of how much each move is worth. Depending on the state, if somebody has 2 in a row, how much do you need to bid for the next move? Let's be more specific. Let's say I have 2 in a row, and I have $400. How much do you need to bid? 401. One of the ways that this game could have a problem is you could just have an infinite string of equal bids. So sometimes what they do is they have a chip that breaks the tie, and one person starts off with the chip. And if there's a tie in terms of the bid, if you have the chip, you decide, do you want to win the bid or not? If you win the bid, you then give the chip to the other person. I don't like the chip because it makes there be an asymmetry in the game. Right now, in tic-tac-toe, would you rather go first or second? Does it really matter? No. If you're playing me, it doesn't matter. If you're playing, say, a 6-year-old, does it matter? No. 6-year-old, yeah. You can beat 6-year-olds. I have faith in Williams students. If you're playing a weak opponent, there's a good chance they'll make a mistake, and if you go first, you have a significant advantage. If you're playing 2 really good people, it doesn't matter. Tic-tac-toe, ESPN, even the Ocho, doesn't televise tic-tac-toe tournaments. All right, at least somebody's getting the Ocho, yes? All right, good. Excellent. All right. So the other way to play tic-tac-toe that's interesting is Gobble Tic-Tac-Toe. How many of you have seen the Russian dolls where you have a big doll and then a small doll inside? So the way Gobble Tic-Tac-Toe works is you have 3 sizes, the large, the medium, and the small, and you have 2 of each. And on your turn, you can either put down one of your pieces on a square, or you can put down one of your pieces on top of a square that's already occupied and gobble up something. In some variants, you can actually pick up a piece of yours that's on the board that has gobbled something and move it to another square. There are times when it's strategically in your best interest to gobble up your own piece to upgrade its defenses to make sure the other person can't take over that square. So there was one great game I played years ago in a senior seminar here where one of the students figured out that if he didn't gobble up his own piece, I would win in 2 turns. That actually went into his letter of recommendation, that he was able to figure out in real time, a game he had never seen before, how to analyze something like this. So one of the things I'm trying to give you here is tools to attack a variety of problems. Break things up into small cases and then try to build it up. And so here, these are new games. They're built on things you've seen before. All right, so I quickly assembled, because amazingly the sets here don't actually have 2x4 bricks. So I assembled some 2x4 bricks by using 1x4s and putting connectors in between. How many ways do you think I can put two of these pieces together? So this is now becoming a more challenging problem. And then we'll stop after this. So we have two 2x4s. So you want to find a really good way to enumerate all the possibilities so you don't miss anything. What's the simplest way to connect them? On top of each other. That's one. What else could I do that's similar to this? I could shift it up 1. I could shift it up 2. Could I shift it up 3? So is shifting up 3 different than anything I've seen before? Is that the same as shifting it up 1? Or is it different? I think it's different. So having it connected, shift up 1, shift up 2, shift up 3. What about shifting up 4? No, okay. Then it will no longer be connected. So how many ways are there to have one directly on top of the other? Do we get 4? Okay, so on top plus shifts, okay, is 4. What else? Okay, so which way do you want the sides? Like this? Okay, so we could do a side like this. Is that different than a side like this? So here, we can just rotate those two. So at least in that special case, they're the same. So that equals 1. What else could we do? We could shift it up 1. That's the same as the one down here, but it's not the same as shifting it like this. So we have to double count this shifting up by 1. We could also shift up by 2. We could shift up by 3. What I think is actually easier is to just say there are 4 possibilities, double count, and then subtract 1 because we shouldn't double count this one. So how many possibilities does this give us? 7. So let's say parallel side plus shift is 7. Right? What could we do next? Yes, now I could do 90 degrees. Now it becomes more interesting. We could do it like this and then do all the shifts. Then we could also move it over 1. We could move it over 2. We could move it over and keep going and then worry about double counting and whatnot. So I'll leave the rest of it as an exercise. To just go through and figure out how many ways can you combine them. The question is, how rapidly does this sequence grow? We've got just 2 2x4 bricks. What if I had 3, 4, 5, 6? Do these numbers stay small or do they go fast? How fast is fast? And so they go extremely fast. There's been a lot of nice papers, and I'll send references later as to how you would count how many ways there are. And there's a lot of really good mathematics behind this. How many of you have heard of Ramsey theory or Ramsey numbers? All right, so this is a really nice way of talking about how large things can be. So a lot of times in math, unfortunately, we can't prove the actual value, but we can get bounds for it. So let's imagine that friendship is symmetric. If you like someone, they like you. This is not necessarily a reasonable assumption. So you could maybe say, if I know someone, they know me, if you want to do it that way. All right? So the question is, how many people do you need at a party before you are guaranteed that there's a subset of 3 such that everybody in that subset knows everybody else in that subset, or no one in that subset knows anyone else? Give me a really weak bound on how many people you need.
3.
Well, you have to prove that. You need at least 3 people. right? If you only have 0, 1, or 2 people, you're not going to have any subset with 3 people. So imagine you have 3 people. We'll connect people if they know each other. Is there a way to assign friendship? We'll connect them, I guess, if they're friends. Is there a way to assign friendship so that you do not have a subset of 3 who know each other, and you do not have a subset of 3 who don't know each other? So how could I connect them so that there's no subset of 3 that all know each other, and there's no subset of 3 that don't know each other?
Just connect like the bottom 2.
Yeah, connect the bottom 2. So we need to have at least 4 people. All right? Well, what if I have 4 people? If I go like this, is there any set of 3 that all know each other? Is there any set of 3 that don't know each other? And the easiest way to see this is I have to choose at least 2 from the bottom or at least 2 from the top. I've got to choose 3 people. Another way of saying that is I have to leave 1 person out. So either leave 1 person out on the top or 1 person out on the bottom. So you need at least 5 people. With a little bit of work, you can show that there is a way to assign friendship so that 5 people don't work. But with 6 people, there will always be at least 3 who know each other or 3 who don't know each other. And so that is called R33. It's the number of people we need so that there are either 3 people who know each other or 3 people who don't know each other, or 3 people who are all friends or 3 people who are not friends. And so this number is 6. So one of the interesting questions is, how quickly does this number grow? We only know a couple of small values. This is a very famous open problem. We have bounds, though, on how quickly it grows. And some of these bounds are incredibly large. Exponentials of exponentials of exponentials, and we think the answer is 6. They grow extremely rapidly. How many of you know who Paul Erdős is? Okay, how many of you know who Kevin Bacon is? Okay, do you know the Bacon game, the Oracle of Bacon? So have you been in a movie with somebody who's been in a movie with somebody who's been in a movie with Kevin Bacon? If you're in a movie with Kevin Bacon, your Bacon number is 1. If you're in a movie with somebody who was in a movie with Kevin Bacon, your Bacon number is 2. Years ago, I got my brother by having him go from, I think, John Belushi to Kevin Bacon, and my brother forgot that they were in Animal House together. So it was a really easy path. He was trying to go through all these convoluted things before he finally realized, oh wait, Kevin Bacon is one of the fraternity brothers. He's been in an enormous number of movies. Most actors, and you can go back to obscure French early 20th century actors, you can get to Bacon in 6 or less. It's incredible. In math, we have the Paul Erdős game. Have you written a paper with Paul Erdős? Have you written a paper with somebody who's written a paper with Paul Erdős? So my Erdős number is 2, my kid's Erdős number is 3, any student who writes a paper with me has an Erdős number of 3. Paul Erdős, to try to give you a sense of the computational complexity of these numbers, said something roughly of the following. Imagine an alien war fleet appears in low Earth orbit and says that unless we give them the value of R55 in a year, they will obliterate our civilization. We should devote all of our resources to computing this. If, however, the aliens want R66, we fight. In terms of the computational complexity, we are nowhere close to being able to pin down what the answer is for this problem. Okay, so I think this is a good place to stop for today. Again, the whole point of this was to use these as springboards to see some good mathematics behind it. For those of you who are considering quantitative careers, I strongly urge you to look at the technical papers I will send later today. All right, so for the rest of today, I want to just talk with the LEGO Ideas people and then just quickly coordinate with the West people as to what we're going to do. Okay.